Hello everyone, welcome again. And in the last lecture we were talking about functionals and how to take derivatives of functionals, and in this lecture we are going to talk about Lagrangians and least action principle, and the concepts that we learned in the last lecture will be useful here. So if you haven't seen that, I highly recommend you to watch that video before entering further in this. Okay, so firstly we will consider two things. The first is the potential energy that we generally write with the letter V, and we say that it's a function of x, and the kinetic energy we normally write it with t, and it's a function of the time derivative of x because it's simply equal to half mv squared or half mx dot squared. X dot means the time derivative of x. I hope you all know that. And now we are going to consider two things. They are the average potential energy and average kinetic energy. So the average potential energy, I am writing that with V bar, and this will be equal to integrating V of x respect to time from 0 to some time tau and dividing that with tau. And now the x is also a function of time. X is actually a function of time, so we can say that this is nothing but a function of x. Okay, and also the average kinetic energy, that's a function of x dot, or we can say x, where x is in a derivative form in the expression. So this becomes half m x dot squared dt. Yeah. So now, as we have written the average potential energy and the average kinetic energy, we are now interested in seeing how they change if we slightly change the path of the particle. And x is the position of the trajectory of the particle at some time t along the trajectory, and we are going to differentiate these using functional derivatives with respect to x. So first let's differentiate this thing. We are interested to find this object. Okay, so I calculated one expression in one of the examples in the last video, and I'm writing that again. If there is a functional h of f that looks like this, then the functional derivative looks like this thing. And we are going to use this expression here. Here V bar is the h, x is the f, t is the x naught, and g here is the potential V, and f is x as we, and yeah. So here this thing will be equal to 1 over tau. This thing will be just get outside of that derivative, and then we will have V prime of x at t. Okay, so yeah, this looks like the same just look like this. G is V and f is x is t, and like that. So we used this expression to find out the functional derivative of the average potential energy with respect to the trajectory or the path or the position. So this tells us that when we slightly change the trajectory of a particle, how the average potential energy changes. Okay, so similarly we are also interested in seeing how the average kinetic energy changes when we slightly change the path. Okay, so now we are interested in finding what this expression will look. Yeah. So here I also did another example in my last video that's like this. If j of f is some this is ty. Yeah. If this is the functional j, then the derivative will look like this. Okay. Yeah. So in our case, this will look like exactly this thing. It will be there will be one minus, there will be a 1 over tau, and the expression will look like this. This is just analogous to this one. Okay. Yeah. Mx dot is nothing but differentiating this thing with respect to x dot, so that the 2 will come back here and it will cancel the 2 in the denominator. So we will have mx dot, and that's I've written here, and this will be equal to minus 1 over tau mx double dot, keeping in mind that our m in this case is constant. Okay. So I'm going to erase this. So what we have got here is how the potential energy and the kinetic energy, the average potential energy and the average kinetic energy change when we slightly change the trajectory of the particle. And we will see that these two things are equal if the particle is following the equation of motion. Okay, so let's see that. From Newton's laws, we know that the force is negative of the differentiation of the potential, or we can say it's the negative v prime, and force is nothing but mx double dot. So mx double dot will be equal to minus v prime, and if you see carefully, v prime is what we have got here and mx double dot is in this expression. So we can replace mx double dot with negative this thing and v prime with another negative of this thing. Sorry, v prime is this thing. This minus sign will be here, and another minus sign will come here, and they will cancel each other out. So then we will be with this object. Yeah, and tau is just an arbitrary number or time, so we can multiply it 1 over tau to the both the sides, so it will not create any problem. So what we have got here is telling us that if we slightly change the trajectory of the particle, the change in the average kinetic energy and the average potential energy will be equal if the particle is following the equation of motion. Okay, if the particle is following this equation of motion, then we will get this thing as our answer. Okay, so I need to clear this thing. Okay. Now some interesting results we will be encountering. So from this expression, if I take the right hand side to the left, what we will have is this thing. Okay. So if the particle is following the equation of motion, then the difference between the average potential energy and the average kinetic energy will remain stationary. That means that it will not change with if I change the trajectory. Yeah. And this tells us that this difference between average potential energy and average kinetic energy is something special. And I'm just writing the expressions now. We will see that there will be some quantity t minus x, that is the difference between, t minus v, that is the difference between the kinetic energy and the potential energy. And this is just the integration of kinetic energy with respect to time, and this is integration of potential energy with respect to time. So we can take the integration out and we will have this thing. I will be writing that. But this difference is the special thing, and we will call it capital L, which stands for Lagrangian. Okay. So now we will write this thing again. This thing is the 1 over tau 0 to tau t dt, and this will be 1 over tau 0 to tau v dt. So I can just take it inside this integral. This will look like this. Okay, so I can take 1 over tau out, and I can just take it to the right hand side and multiply with 0, and I will get 0 also. So what we get here is this thing. Replacing t minus v with L, we are getting this interesting expression, and we call this integral the action functional, and we denote it with S, the capital S. Yeah. Where S is equal to integration L dt from some point A to B, or in this case 0 to tau. And this expression tells us that if the particle, okay, let me change the color, if the particle is following the equation of motion, then this thing will be 0. And that's why we call it the principle of least action. When we set the derivative of some functional functional equal to 0, that can happen in the critical points that can include the maxima, the minima, the saddle points. And in this case, the term least action is somehow stuck in the textbooks, but more generally and more accurately speaking, this is called the property or the principle of stationary action. Yeah, so critical points are also called stationary points. So if we know the action of a particle or any object or any quantity, then we can find out its equation of motion if we set the stationary action principle here, if we set the functional derivative equal to 0, and that gives us the equation of motion. And yeah, so that's kind of wonderful, and it's also called the Hamilton's principle of least action. And now I am interested in finding the expression in general without writing t or v, but in terms of the Lagrangian. So we will find that now. As S is equal to just integration of L with respect to time, so this will be from some point A, or from let me write Ti, initial time to final time, this thing. And later we will set it equal to 0 to get the expression. Now, the Lagrangian L is made up of the kinetic and the potential energy terms, and the kinetic energy is depending upon the time derivative of x, and potential energy depends upon x in our case. And so we can say that Lagrangian in general is a function of x and x dot. Okay. So we can use the partial differentiation rule, the chain rule of partial differentiation here, and we can get the expression at some time u, where u is in between Ti and Tf, plus this thing. And now this quantity is nothing but the Dirac delta function, and we will be treating this quantity also using Dirac delta functions, but with a little trick. So I am going to write again the first term is nothing but this plus here x is differentiated by time in this term, and here it's functionally differentiated by x at time t. So the two differentiations are not related to each other, they do not depend upon each other, so they can commute. Like I can take the functional derivative first, then take the time derivative, or I can take the time derivative first, then take the functional derivative, and it will give the same answer. So I am taking the time derivative out, and inside I will have delta x of u by delta x of t, and that will again give me the Dirac delta function, this thing. Okay. The first term is this, and the second term is this. Yeah. So I am erasing these first two lines. I have a very small board. Okay. So, using the properties of Dirac delta functions, as u is somewhere in between Ti and Tf, and we can write this as delta L by delta x of t, right? And now this integral we are going to do by parts. We are going to do by parts. Yeah. The first term will give this thing at Ti and Tf u, at T at Ti and T at Tf, and the second term will give this. Now, a similar situation we saw in the previous lecture, where we were doing by parts to get, I think the expression that we used in this class is where in the derivation of that expression we used something related to the by parts integral. Okay, and now when t is equal to Ti and t is equal to Tf, this thing will give 0 because u is somewhere in between them, not equal to them. So this is 0. So we left with that, and once again our Dirac delta functions is not anymore inside any derivative. So we can use the property by replacing all u's with t, and we will get something like this. Yeah. So this will be my functional derivative of my action. And according to the stationary action principle, we need to set this thing equal to 0 to get the equation of motion. So here, what we have just derived is the famous Euler-Lagrangian equation. This is called the Euler-Lagrangian equation. Well, if you have done functional methods in your mathematical physics class, you may have encountered previously with these things, and also something called the least path on a plane is straight line. Perhaps you have proved that earlier in your studies, and if you have, then you will see that a similar kind of equation arise in that case also, and that's called the Euler equation. As per I remember, that can be Euler something else equations, someone else's name can be up there, but I cannot recall at this moment. But I have not included that part here because it will not be of use today, and I highly recommend you going through some of your mathematical physics textbooks, and one of the textbooks that I can refer you is the mathematical physics for mathematical physics. I think the mathematics in physical sciences, the name of the book is, but the writer is Marielle Boas, so you can look it up there. She gives a wonderful explanation for all the methods that I am using here. Okay, so we have got the Euler-Lagrangian equation, and the Euler-Lagrangian equation will give us the equation of motion if we know the Lagrangian, and the Lagrangian of a particle is nothing but the difference between its kinetic and potential energy. So if we know its potential energy and the kinetic energy, we can find out the equation of motion by just putting the Lagrangian into Euler-Lagrangian equation. So it's like a wonderful thing, and it's pretty easy than finding the equation of motion from Newton's laws for complex situations. Okay, so now we are about to define another quantity called the Lagrangian density. Lagrangian density. We can write the word the Lagrangian as some integral of the Lagrangian density. Remember, this is in one dimension. In 3 dimension, there will be 3 derivatives here, d cube x. In 1 dimension, it will be dx. So Lagrangian density is nothing but the Lagrangian in unit space. So in case of 1 dimension, the Lagrangian in unit length. In case of 2-dimensional system, the Lagrangian density is Lagrangian in unit area, and in 3-dimensional cases, the Lagrangian density is Lagrangian in unit volume. And in 4-vector cases, it will be the Lagrangian density. The Lagrangian density will be Lagrangian in unit volume in 4-dimensional space-time. Okay. So in terms of Lagrangian density, my action will look like this for one spatial dimension. And I am going to use this thing to show you an example, and yeah, and I will show you that the fun is that I can use a Lagrangian density to find equations of motion instead of the Lagrangian. So let's go into it. It's very beautiful and tricky also, so we need to put some extra care while learning it for the first time. Then you can practice it and get familiar with the ideas. Okay, so we are considering a string. This is a string, a thick string with some waves in it, and the string has mass m and length L. I'm going to write small l, and its mass density or mass per unit length is m over L, and there is some tension tau in the string, and the amplitude from equilibrium position is psi. That will be some function of space, position and time. Yeah, and the kinetic energy of this string is defined to be this thing, and the potential energy is this thing. Okay, so now our action is dt times L, which is nothing but the difference between t and v, and we can write this as dt dx of the Lagrangian density. And in this case, the Lagrangian density will definitely be some function of psi itself, and in previous case our Lagrangian was a function of position x. Here we have replaced x with psi because this system is depending, the variable in this system is psi, and it will also depend upon the time derivative of psi because psi is changing with time and we need to consider that, and it will also depend upon the space derivative of psi. Because along the x direction, psi has different values at a single time slice. Okay. So in this case, if we put these two expressions here, we will get our Lagrangian density So this will be our Lagrangian density, and using least action principle or stationary action principle, here the variable is psi, not x anymore, we will see that this will be equal to this is the thing that we have got previously in our Euler-Lagrangian equation, but as it is also a function of the space derivative of psi, another term, similar looking term, will be here. And you can check this using the functional methods, the functional derivatives that I taught you in previous class and in this class. So this will be my least action principle, and the Euler-Lagrangian equation will somehow look like this. And now, as we know the Lagrangian density, we can just put these values here by differentiating the Lagrangian density. Firstly, the Lagrangian density, it doesn't depend upon psi anywhere, it depends upon the time derivative of psi and the space derivative of psi. It doesn't depend on psi anywhere in this particular case. So this thing will be 0. Oh, let me just change it. This thing will be 0, and if we differentiate by the time derivative of psi, this thing is here, so it will give us this thing, and similarly that part give this thing. Okay, and this is equal to 0, so I am writing again. This is my equation of motion. The fun thing is, we all know that this is a wave, right? There can be waves on a string, and this is the equation of motion of a wave with respect to the mass density, linear mass density, and the tension. And we also know that a wave must follow the wave equation. The wave equation looks like this. And if we compare these two things, we will see that the velocity of the wave will be root over tau over rho. And this is the expression that we have been learning from our high school days, from our class 11th or 12th. We are seeing this expression that velocity of a wave on a string is the square root of the tension divided by the linear mass density. And yeah, so using the Euler-Lagrangian equation and using the concept of Lagrangian density, we can see that we can find out the equations of motion. And in this case, we just verified that the velocity is indeed root over tau by rho. And yeah, now I am going to erase this thing. Now we will see the 4-vector representation of Euler-Lagrangian equation using Lagrangian density. We have seen in Lagrangian density, the Euler-Lagrangian equation not only contains the time derivative, but also contains some space derivatives. Okay. So together we can say that it contains some 4 position derivatives. 4 position means this thing. And if you do not know about these things, then you need to take some special relativity classes and some tensor classes to understand the index notations. I will be using index notations and Einstein conventions. So I recommend you to study that before. There are plenty of reference books out there, and also lecture notes are out there, so it will not be any problem. So our action will now, that integral will be over d4x, because there are 4 dimensions here, and the Lagrangian density will be a function of some amplitude. Previously we have seen that psi is that amplitude, and also some derivative of psi, of phi in this case. Mu goes from t, x, y, z, so this contains all possible derivatives of phi with respect to t, x, y, or z. Okay. And the Euler-Lagrangian equation that was previously like this, okay, just a minute, let me change the color. previously it was like this, but now our variable is not anymore x, but now it's phi. So the Lagrangian density will be looking like this. There will be some term like this, and this term here contains only the time derivative, but now we have all kinds of derivatives in here and also in here. So this will look like this. So this will be my Euler-Lagrangian equation in terms of 4 vectors using the Lagrangian density. Yeah. Yeah. Okay, so let me give you an example of how to use it. Suppose we have some Lagrangian density like this. We can find the equation of motion by just putting this thing in this equation, and what we will get here, this thing will give minus m square phi, and this thing will give del mu phi, and togetherly we can write minus m square phi plus del mu phi, sorry, minus, there is a minus here, it's equal to 0. So we can write the equation of motion like this, or this term can also be written like del square, so we can write it like this. And this is the equation of motion if a Lagrangian density looks like this. And this is, if you have previous knowledge about this, you may know that this equation is nothing but the Klein-Gordon equation, and we will see later about this equation a lot. But yeah, today we just saw how to use the principle of stationary action and the Euler-Lagrangian equations to find out the equations of motion. Okay. Yeah. So bye for today.